welcome to the AI for You Cafe for our live presentations around AI. As always, we go slow because the people are entering the cafe. But already I can welcome Wouter, Denayer, the CTO for IBM Belgium next to me. And hello, Wouter.
Hello, Carmen.
Hello. So I will, as always, first introduce the cafe, and then we come to the speaker, and we give everybody the chance to enter the cafe. So please take notice that this cafe session will be recorded. No confidential information shall be shared in this cafe session. In this cafe, the speakers express their personal view and opinions. This is not necessarily the official AI for You project opinion. And again, what is this web cafe about? It offers a series of live web sessions which will take place regularly. The cafe is an online forum to gain insights into the European AI scene. Participants get the chance to share knowledge and experiences and meet stakeholders from various areas of AI research and application. And as you always know, there's a chance to ask questions. There's a control panel on your right side, so you can type them in during the presentation, and then I will read them to Wouter after the presentation, and we are looking forward for your input. And now we're coming, of course, to the reason we are all here. Again, welcome to everybody in this cafe. It's great you're all there, and it was a long summer break, and I hope you had this great summertime. And now I will introduce my guest. Hello, again. Hello, Wouter. Hello.
Hey.
Wouter is a technology optimist. He's on a mission to strip away both hype and fear surrounding artificial intelligence so that its true potential for society and business can be realized. With a degree in linguistics and literature to balance his inner geek, he architects IT solutions that actually deliver their promised value. As CTO for IBM Belgium, he feels privileged every day to work with a diverse and global team of wonderful colleagues. Oh, that sounds nice. So, okay, welcome, Wouter, Denayer, and I give you now the moderator role, and you are now able to share your screen and welcome and introduce yourself, and great to hear.
Okay, well, thank you, Carmen, and thanks for having me. It's a privilege to be here to speak to all of you. Maybe we can meet at some point for real. That would be fantastic, in a real cafe. But you're totally right. I am a technology optimist, and I am very excited to talk about what IBM is doing in the space of AI. So we are ahead and have been doing this for a long, long time, much longer than since I joined the company. That's now 20 years ago that I'm with IBM. So that makes me, I guess, no longer a junior employee. But it's been a fantastic ride for me. And the last, I would say, 5 years, I've been working more closely with my research colleagues, and also, trying to understand and speak about how we see the future, where technology is taking us. And of course, nobody can get around AI. That is clear. That is, of course, the main topic that everybody is talking about, and the main topic for today. So what I will do for you now is to, what I want to do is to actually share a view on the future of AI. It is let's say, my view. It's my selection of things that I find interesting and my storyline through that. So I will take you through a little adventure here, and I hope you like it, because this is important, right? I mean, we expect a lot from AI. There are also some fears that are still going on. I don't know how about you, but I still hear a lot of people that don't really trust this technology. And so I want to demystify this a little bit, because I think the promise is immense. also to take on big challenges in the world. I mean, we will not be able to do that without technological support and without AI being part of that mix. And so when I see then, press releases such as this one, titles on websites, and that say, okay, OpenAI built this text generator and it's too dangerous to release. Okay, what does that mean? Is it fear mongering, or is there some reality to that? And the focus word, of course, is this: too dangerous. So this is a quote from February 2019, and it was in the context of an AI system that the OpenAI company released called GTP2. And this system is able to generate text. And I will give you some examples of that, but it can automatically write, if you will, write texts that are readable. And I will come back to that, what I mean by that. And so the fear that is suggested is not so much maybe about some evil AI system that will take over the world, but it's more about too dangerous because it could create a lot of automatically generated fake news. And of course, we have enough of that already. We don't need more fake news. So maybe that is why it is too dangerous, but it's certainly not in terms of general AI or self-thinking systems, something that was a little bit suggested by OpenAI, but that is absolutely not the case, and I will also show you why. So it was too dangerous to release, they said, and then they started to release it anyway. First a small version, a somewhat bigger version, and then a larger version. And so how this thing works is it reads millions of web pages, and what it basically can do is it can decide what the next most probable word is. So if I give you this example, and it will also show you a bit how dangerous I think this actually is. If I show you this sentence here, it's a little children riddle. I invite you all to try to find the answer. The 6 frogs to leave, 3 join, and the answer, of course, is. You cannot answer, Carmen, because you know the answer. That would not be fair. And the answer, according to this fantastic AI, is 17. Now, if you didn't miss all of the mathematics classes in school, you know that this is not the correct answer. And so something is clearly missing here. So the AI is able to, yes, complete the sentence. And at first sight, it is indeed, it's a number there. We expect a number. So I guess, we can give some points for that. But in essence, of course, the answer is totally wrong. And it points out that it does not understand at all what is going on in the sentence, right? There is no understanding. It is just using statistics to try to find, what is the most probable word that should be put after this sentence. So there is no common sense, there's no understanding. So in that sense, there's no need to be afraid. I will give you another example here, which is also very interesting. So how this thing works is, again, I give it a begin sentence, and my begin sentence, the one I give to the AI now, is Alan Turing was. And I ask the GPT-2 system to complete the sentence. And that's what it's doing right now. So it's completing the sentence, and I give you just a few seconds to read what's going on here in that sentence. So if we look at this sentence, you would probably agree with me that it sounds rather good, right? I mean, it's readable, it's grammatically correct, it sounds, interesting. There are facts in there. It's not bad. It's about Alan Turing's life, and it's giving us some information. But let's look a little bit deeper and scratch a bit behind the surface of this sentence, and we will see that it's totally wrong. Actually, the date of his death is wrong. His age is wrong. The way he died is wrong. This honor he did not get. He did get another one, but not this one. And then, of course, the one that he got was not for this work on the nature of intelligence. So we can say this sentence is indeed interesting in terms of fake news, right? Because it looks correct at first glance. And if you don't have a history background on Alan Turing and you maybe read his biography, I can highly recommend that, or watch the movie, of course, which is fantastic. Then if you don't have all that background information, you can be fooled. That is really that is so. And so we also built at IBM a system to detect this auto-generated text. So, and that's what's going on here. So what you see now is a coloring of the same sentence, and the parts in green are the parts where our, detective AI is unmasking that the green words are most likely to have been generated by an AI system. So we can actually say that you see a bit of an overview here, that most of the words are in green. So we consider most of these words to be auto-generated. And on top, we have a high confidence rating. So the confidence 1, which is on the right of the gray histogram that you see. So there is some truth there, in a sense that it does generate texts that look rather good, and we have to be careful. Now, that being said, this system here, if you use it, and I did, I actually installed it and I tried it out, and more often than not, sentences are coming out that are unreadable and that you immediately detect. So it's not perfect at all. And I will get a little bit later back to the point that they have created a new one, which is a little bit better, but still missing common sense. But the interesting part is of these transformers, these text generators, okay, we can use them in creative ways. And I wanted really to show you this because I find it's so innovative. So if we look back at chemistry, I'm taking you, through all your classes from school. If you look at chemistry, you know that you have some reactants, some basic molecules that we mix up. We put them at some temperature, we stir them. These are our reagents and conditions, and we get some chemical result. Okay, that is, of course, the basics of chemistry. But what if we represent all of these steps by text? These are encoded, so I encode the same, chemical reaction, but I put it in texts. So now you can see that I can also use text completion, right? Because I can use the part before the plus and then the part after the plus. I can use it as the begin sentence, if you will, or text string, and I can ask the AI to complete the text. But in essence, what it's doing, it's completing, it's predicting what the chemical reaction will bring as a result. Now, this is super interesting because it means I don't have to run the chemical reaction. I can do this in my computer. I don't have to go to my lab, and go through all the steps of really trying out the reaction. I can do it in my system and have a simulation, if you will, of the chemical reaction. And so we use this type of AI as one element in this system that we built. And that is being used, for example, today in a COVID context to try to find molecules that could be active against the virus. And instead of trying everything out in a real lab, in vivo, we can actually limit the number of drug trials, drug tests that we have to do to try to find a solution here in terms of active against the virus. So this is one example where AI can help speed up the creation of medicine. And so this is actually very, very promising because a lot of time is lost because the labs try, reactions that don't work, that are not effective. So if we can narrow it down, if they can be more precise on what might actually work, there's a huge gain to be had in terms of speed and, of course, also investment. Now back to our AI system that we saw before, so the text generator. I want to show you how this thing evolved. So in terms of neural networks, which is of course the core AI system that everybody loves to use now, and deep learning, we talk about the number of parameters, that the size, if you will, of the neural network. We can express this size in a number which represents the number of parameters. And so the OpenAI example I gave, they released a small version a medium version, and then the large version. And the large version was 1.5 billion parameters large. And so this was considered back then, February 2019, or this was a bit later, maybe already, a huge network. But people started pushing this because the idea was the larger we make the network, the more correct it will be. And that was the assumption. So actually what they did, they built a new one. This one a bit later by another company, in this case Microsoft. They built one 17 billion parameters. So this is already 10 times the size of the OpenAI one. And then OpenAI, not to be outdone by Microsoft, I guess, they created a new one, and now the latest, greatest, and biggest and largest neural network in the world is 175 billion parameters. And that's the next version of OpenAI, GPT-3. It was trained on 500 billion words. 500 billion words. These are numbers that are too large for me to comprehend. I mean, we cannot grasp that anymore. And the thing is, it's a little bit better, yes, at completing sentences, but it still does not have any common sense. So the part where it's not understanding the phrase and completing just because it doesn't understand is still there. So it turns out that making the networks larger and larger and larger is basically not helping us getting closer to a system that has common sense or closer to this holy grail that is general AI. So it's clear that this is not the path that will bring us there. I mean, we are now at 175 billion parameters and the AI just makes stupid mistakes still. And that does not mean, again, that it's not useful. Don't get me wrong, it's useful in translation, it's useful in the chemistry example and so forth, but there is no understanding and will be stupid errors being made as well. And so having these larger networks has another big problem. And the problem is that it takes an insane amount of energy to train them. It's mentioned in literature that one of these large networks, and that's even before the super large one that I just showed you, took the equivalent of 5 cars with their total pollution. So the 5 cars over their whole lifetime, so the whole lifetime of a car, and all the pollution involved in those 5 cars was needed, or this amount of pollution was created to train this network. And on top, it's really sad, I would say, only a 0.1% accuracy increase was achieved. So again, I hope you see that making the networks larger and larger per se will not help us, and on top gives us, I would say, a sustainability and energy problem. So we really need to do something about this. We need another way to get to common sense, and we need to fix also the energy problem. Both are very important. So let me start with the first question. How can we be more energy efficient? And at IBM, we are working on new hardware for AI. So we can build these large networks, yes, that we can train them because they will be useful, but we want to do with less energy. And we work on 3 different lines of thinking. One is what we call bits. Just consider that as the classical computing, the classical processing power in a normal processor and a normal computer that we will enhance. They will become faster, they will become bigger. So we have to work on that clearly. We have to put some AI capability in those classical computers, which we are now doing. So that we have to do. So that is the first element. So these bits, as you know, at IBM, we built some of the largest supercomputers in the world, and they've turned out to be very useful again in COVID times now to speed up simulations. How does a molecule interact in the presence of a virus? These are simulations being done on insanely large supercomputers. So that's an important part where we push the frontiers. Second one, you may have heard about quantum computing, and really, Carmen, this could be the topic of another session by itself, because this is absolutely fascinating. If we succeed in creating a quantum computer, then it will become possible to do simulations like in chemistry, for example, or in optimization problems that are totally impossible today, even on the largest supercomputer in the world. So there is a class of problems that cannot be solved. And we give this example, like if you take a caffeine molecule that's in your coffee, of course, if you want to simulate the way that the electrons are flowing around this caffeine molecule, today it is impossible to do with sufficient accuracy. And this is a very simple molecule. And in the end, if you dream, what you would like to do is to simulate, I mean, let's take COVID, right? You would like to fully be able to simulate how a drug interacts with the virus. Fully simulation in the computer without going to the lab. That's our dream. And this will not be possible with classical computing. We need to move to qubits, to quantum computing. It's a new class, and it's mind-boggling. And today the systems are not large enough, so they are not. I mean, we cannot use them for practical problems yet. But just yesterday, just to give you an example, at IBM we announced our roadmap for quantum computing to go to 1,000 qubits in 3 years' time. And so I was surprised because I didn't even think it was going to be that fast. So this is going to become mainstream and really, I don't like the word, but game-changing, I think in this case is appropriate. Between 5 and 10 years from now, this is going to be huge. Also for AI, because you can consider the training of a neural network, for example, as an optimization problem. And so also there, the quantum computer will be able to help. Great. And the part I want to spend a little bit more time on here is actually neurons. And we know everybody's using graphical processing units and GPUs to accelerate neural network training. They are very, energy inefficient, and they use a lot of electricity. And so we work on a new system, which is analog in nature. Yes, you're hearing that right. So we are going to use analog chips. So we will have calculations with basically electricity. So no longer bits and bytes, but using the laws of electricity, Ohm's law, for example, to do the typical calculations involved in training a neural network. Multiply and add are always there. And these chips, they are going to be amazingly energy efficient. So that is what's so great about them. So we believe that they can be, I think 100,000 times more energy efficient than a classical chip. So this is an example of an accelerator. It will be useful for AI. And we solve one of the, just to give you an idea, one of the problems that we solve is what's called the von Neumann bottleneck. It's the pipeline between the processor and the memory. Right? We all know in a normal computer, you have the processor and you have the memory, and you have to copy the data into the processor to do work, to make calculations. This takes time, and this is a bottleneck. Okay, so a lot of the time the processor is just being bored and waiting for the data. And so what we did here is we put the calculation itself in the memory. So there is no bottleneck. They are together. They are one and the same. Calculation and memory are the same, so you don't need to move it around. And that's why you can get an enormous speed up in terms of time spent, but also an enormous reduction in energy consumption. So this is very promising. This is in the lab. You cannot go to your computer store and buy this yet, but this is something that I think will come very soon. And this is some very clever designs that they're using, working with the conductivity of certain materials. So this is one way we are trying to fix the energy problem. So the fact that the training of these networks is just too expensive and too polluting, to be frank, and also not fast enough. So this is analog computing, and it will be probably 100 times faster than a GPU card. Which is kind of cool. Secondly, as I said, we need to work on the other element, which is common sense. I mean, as long as we don't get AI systems that we can trust, in the sense that the answer I get is correct, not the little, the riddle that I showed about the frogs. I mean, this one I can solve myself, and I say, okay, your result is not correct. But if I give it a more complicated problem, I should be able to trust the result that I get, right? And today, that is not the case. So we need another paradigm shift to get there. And to explain what we are doing there, I will go back a little bit into the past to Alan Turing again. Alan Turing, of course, is one of the great founders of computing as we know it. He created the Turing model for computation, and he imagined a system with an infinitely long list or tape of instructions that could be processed. That was his thought experiment, and of course that came into reality. What he also did was he created a chess program. So from the beginning of computing, there has been, of course, the fascination with creating an AI, and what better to represent human ingenuity, creativity, and intellect as, of course, the chess game, which is complicated and, of course, was thought for a long time to be impossible for computers to do. But still, they started on that. He created a chess program called Champ in 1948. They didn't have computers fast enough or powerful enough to actually run the program. He actually he wrote the software, if you will, but the hardware was not there. So they, in the end, they played the game on paper just to try it out. And it took half an hour to calculate the next move of his Champ program, but they played the full game doing that. Of course, later on, as a side note, Garry Kasparov played against a real implementation of this algorithm, and of course won. That is clear. But that was a fun experiment they did, I think, at the celebration of Turing a few years ago. But the main element here I want to get to basically is symbols, because one of the big breakthroughs in information theory is the realization that we can actually represent through bits and bytes all symbols that we want. And in this case, the symbols that we will be processing are the chess pieces, and we can consider them symbols and we can process them. And so what they did back then in Turing's day, and what I still studied also when I studied AI, there was a lot of attention to expert systems. So the idea is I put all my knowledge into a knowledge base. I describe the world. In this case, I would describe the world in terms of chess pieces and moves that are allowed. And then I would have an inference engine processing the rules. And that is basically my chess engine in this example. And the idea was, in the beginning days of AI, if I create a knowledge base that is sufficiently large, I can actually put all the knowledge of the world in that system. I create my inference engine and have a thinking system, right? I mean, this is also inspired from the brain. We think consciously with symbols. And so that was the thinking. Now it turned out, just to give you an example, this is, let's say we have a Socrates, a human, and mortality. I can have some rules. So my symbols are on top. Socrates, humanity, and mortality are my symbols. I have some rules in my knowledge base. Okay, all humans are mortal, and second one is Socrates is a human, so my inference engine can deduct here a response, of course, and decide that Socrates is mortal. Now imagine systems with millions and millions and millions of symbols and millions of rules. Can we get a thinking system? Now it turned out that this was not possible for many different reasons. One of the reasons is that the knowledge base has to constantly change, has to be updated by humans. It becomes too big. The knowledge base starts to have contradicting data. So, I mean, you have one fact and you have another fact that's saying the opposite. So now what do I do, right? And so it turned out to be just basically impossible to maintain such a system. And people tried. So there is one well-known example called CYC, I think. I don't know how to pronounce it. It started in 1984, and for, I would say, more than a decade, they added symbols to that, 1.5 million symbols, 24 million rules, but in the end it had to be abandoned because you cannot model the real world like that. You can model maybe a simplified world like that, so there are still areas where this is useful, but in the end you cannot. And of course, then what happened is we got the breakthrough of deep learning, where we said, okay, we cannot put all the rules ourselves. We have to have a system that discovers the rules, right? I mean, that is the breakthrough of deep learning. We were able to create them large enough, big enough, with enough data, and then we got amazing results, of course, with deep learning. But as I showed you in the beginning, with the frog example, okay, there are problems there. And you know, I could do a whole talk about ethical problems and bias and racism and sexism and all these things, right? I actually did a TED talk on that one, TEDx in Antwerp. And that is a huge problem. I mean, it's violating not only common sense, but it's also violating societal rules. And we need to fix that because trust is so important in AI, in the adoption. If we don't trust the systems because they give correct answers and because they don't violate the rules that we have set for ourselves in society, then these systems will be limited. So, so what we are doing actually now, and that's why I started with Turing and then showed you the neural network system, we are combining best of both worlds. This is really where the AI research is going now and where IBM is putting a lot of effort. It is combining the strengths of both worlds. It's combining neural networks and their ability to find statistical patterns, to also detect signals in the noise of data, for example. But we are also bringing back symbolic reasoning because there are so many algorithms that we have created, and in the end, we humans think in terms of symbols, and we combine those two. Another big advantage of this is that if we have symbols in our neural networks, we can actually more easily explain what's going on inside of the neural network. We know the black box problem, the problem that we see the decision of the neural network, but we don't know why. If we combine this with symbolic reasoning, we can actually ask the AI to tell us how it came to a decision in a symbolic way. So that is something that we as humans can actually understand. So to give you one example here, it's this one. I'll show you a little movie here, if you will. It's a puzzle. Okay, so again, our Turing, right? And this is a children puzzle. You know, in AI, we use a lot of children examples because they are very hard for computers to solve. So this puzzle is easy for a computer to solve if I give it all the information. If I tell it what the pieces are, if I tell it what the moves are, and if I tell it what the end result is. It's very easy. It's a super easy optimization problem. Shouldn't take longer than a few nanoseconds to solve, probably. But it is very, very hard for a computer to solve if I don't give it all of that information. If I tell it to detect by itself what it has to do. And what I do here is I give it, of course, I give it the initial image of the puzzle, and I give it the target, and I just give it a very small number of examples. And then it has to figure out all the rest by itself. And this is extremely, extremely hard. Because if you know about neural networks, one of the things that's typical there is we give millions of examples to train the neural network. I mean, to do image recognition, for example, I give it, 1,000 or more examples of a cat and of a dog and of whatever, and then I train on that. What we are trying to do here is to have the AI detect by itself and to detect quickly without so many examples. What I'm also not doing, I'm not giving it a playground. I don't give it the option or the ability to try a million times. That's what's going on in some of the examples you see with games where an AI is able to play a game. What happens is the AI basically plays this game, I don't know, 1 million times, 5 million times, or whatever. Okay, and after that, it generalizes, it finds the patterns, and it can play the game. We try to avoid that because, of course, as a human, we don't learn like that. We learn with very limited number of examples. And again, if we can do this with few examples. It's very interesting because it will be faster. It works in areas where we don't have a lot of examples, which are many areas where we would like to apply AI, but we cannot today. And so this is one of the areas where we are using this neurosymbolic combination, combining some part neural networks and some part symbolic reasoning to solve this, in this case, the puzzle example. And I want to give you another example here. And this one we call the Neurosymbolic Concept Learner. And it's, again, I would say a children puzzle, if you will. And this one is able to reason about a virtual world, in this case, where you have all these objects. You have these, cubes and cylinders, and they have different colors. And so we can ask it questions like, what is the size of the cylinder that's left of the cyan thing that's in front of the gray cube? So things like that we can ask. So that's one level. Again, without telling the computer everything up front. So the core idea is we need self-discovery and self-learning. What we can also do, and I think that is rather spectacular, if these objects are moving, suppose I throw or I slide the yellow cube and it bumps into the green cylinder, and the green cylinder in turn bumps into the red cylinder, I can show the AI a number of frames, and then I can ask it what is going to happen. I can ask it what will happen to the red cylinder, and it's starting to deduct, based on knowledge of the world and self-discovery, what will be causality, what will happen to what object in what order to predict actually the end result. So this is another example of neurosymbolic AI. And the last example I want to give, I think is really fascinating. So what you see on the screen here is on the left is our IBM debater software in a nice black box. And on the right, you see a woman who is a debate champion in Israel. So she's a debate champion for, typically in debate settings, human against human. And in this case, we had her debate against the computer. So we have a system here that is able to listen to this opening speech that she is making. So she's making, for example, a 4-minute opening speech on a certain topic. And these topics are difficult topics. These are topics that we as humans don't necessarily agree on. For example, we could say, should cannabis be legalized? It's one of the questions. Should, I don't know, should video games be banned? Should everybody become a vegan? Questions like that. Not everybody agrees, right? We go into debate with our friends and family. And so these are hard problems. What I want to say is it's not a problem that you can calculate. It's not 2 + 2 is 4. It's difficult. So the computer listens to the speech. We can understand and find the concepts, against the symbols, I would say, in the speech. So this is much more than speech recognition, right? This is understanding. I'm always hesitant, but a little bit better than before, what the argumentation is, at least, that she is making. What are the points she is raising to try to, win the debate in the end. Then the system itself can create its own arguments. So it's set up in a way that, if the human is pro something, is for something, the computer can be against, or the other way around. And it can create its own argumentation and then deliver its own speech. So we have a debate going on between a human and a computer. So you can see this is like next generation conversation systems. And we tried it. For example, on one, there was a conference when conferences still happened face-to-face, where we had a live debate. And in the end, the audience could vote who won the debate. And the human debater won. But what is interesting is why. The human debater did not win on content. In the end, the human debater won on ability to convince. So there is still something, you know, in our humanity and our facial expression and the way we move and talk that, of course, we are not convinced by a black box with a little screen on it, and much rather by a human, you know, looking us in the eye and trying to convince us. But in the end, so it was all about. I find this fascinating, right? Just imagine that you are facing a dilemma yourself, trying to figure out your own thinking about something, and you want a counterpart, somebody to spar with, and your friends are not available, maybe, then you could have a debate with this system, and it could tell you, okay, maybe you think this, but here are some other arguments, and so you could get, I think, to a richer understanding of the problem space. And we can all use this in times of polarization, of course. It wouldn't hurt to sometimes look a bit at the other side and to try to understand each other. So this is the third example I wanted to give about neurosymbolic AI. And to end my talk, and then I will be happy to go into Q&A with you, I wanted to show you this. It's a quote, of course, by Pablo Picasso. It makes me smile. I don't really agree with it, I must say. So this was in the 50s, and the computers, of course, were different than now. And I think we are moving forward now. And I think that now computers not only give us answers, but they at least give us hints or areas for further exploration. So it's more than that. They are now getting into the domain where they can really help us. You saw the conversation system. I showed you Debater. I showed you how we use it for finding new drugs. I think we've moved quite far since those days, since the days where this quote from Pablo Picasso was actually valid, of course.
Yes, this makes me smile too. So thank you very much, Wouter. This is very, very deep insight and very interesting, and at the same time entertaining. It was a great talk, and thank you very much. And I, of course, because I'm the cafe moderator, I'm allowed to ask the first question. And then we let the participants ask their questions. There are many waiting. I just want to have, I'm curious, how did you get at all to AI? I mean, you started early, so what fascinated you to go in AI?
Well, as I said, and you mentioned in my little bio, I'm part geek. Okay, so I started working with computers when I was 13 years old. So that's quite a while ago. So this fascination with computers, and it comes by itself. And you want to, this idea that I can create something that thinks. It's the stuff of science fiction movies. And then I got the opportunity at university to actually study this. So we studied at the time, we studied expert systems, which were still hot. We studied neural networks, genetic algorithms, Lisp and these things. So it never stopped after that, I would say. Yeah.
Great. It's now I let the audience ask their questions, and here comes the first. We have many questions, so I cannot read them all, but we start with Emre Sevin, and he asked, is the system developed by IBM that analyzes generated text applicable to languages other than English, and for example, is it applicable in Dutch, and also if it's freely available?
Yeah. So there was a demo I can link to that. I hope it's still up, the demo. And if you want to know more about it, we can surely I can point you to the correct persons. Is it applicable in other languages? I think yes, but it would have to be retrained, right? So it will not be just applicable just like that. But let me figure out more about that system. I'm sure we can find a way. And if it's open source, I don't know. There's more and more. IBM is putting lots of things in Git and that, but I don't know about this particular one. So let us figure out. I will make a note of that.
Yes, And anyway, as in the cafe, as you know, afterwards you can write emails and you can go deeper in the subject. Here, Marian Manone, enjoying your talk. Just a halfway comment. Connections with qubits would be great. Also, to connect AI with fields of quantum computing, quantum cognition, and quantum applications to music and other fields. Do you also connect it to music and other fields?
To music, I don't know. So the domains that we see as main points of interest today for quantum are AI, for sure, or chemistry. So the whole area of finding, for example, new batteries, more efficient batteries, which this could be super useful, right? And finding new paints for cars, for example, that are hard. Maybe that can be, I don't know, recyclable or something. So AI, chemistry, and all kinds of optimization problems. So, for example, think about, I would say the classical example, I guess, is if you take DHL, right, or UPS, or any of these package delivery companies. They have a huge optimization problem. Where do you send all the packages at which time, with how many people? What if there is a traffic jam? I mean, it's a big problem if you want to take all of the elements into account. So all areas where you can use optimization, these will be interesting. The prototypical example is the traveling salesman problem, often given. There is a salesman that has to travel 50 cities, and what is the path through all these cities, which is the shortest path? It is a very big problem for a classical computer, almost unsolvable if you go to a large number of cities, and that type of problem can be addressed by AI systems. So by quantum systems, AI, quantum computing, chemistry, and optimization are the big ones. Music, I don't know. We could think about it. I haven't thought about that yet.
It's just like, it's really, I think the question goes towards structured knowledge and not so structured knowledge, unstructured knowledge. And music is still structured, but sometimes creative.
So we should not forget that quantum computing and classical computing will both remain and will both have their specialty, right? The quantum computer will not replace at all the classical computer. It will be an accelerator, a specialty machine to do specific type of problems.
Yes, thank you. And here I have once more, because I thank you very much, Emre, because I think you're writing 10 questions, but he's at the end. He's fascinated about the free-form debate AI system, which you just showed. Does it need to be trained for a new topic? How much energy would it consume for training? And then for the actual debate, what kind of business problems can it be applied to, according to you? What do you think you can use this debate machine for?
Yeah. So yes, it is trained, but maybe not in the way that you expect. So of course, it needs knowledge about the topic that will be debated, but we are just feeding it text, and it has to extract and detect from all the text that it gets the argumentation. So the points that are pro, the points that are con, it has to group them, it has to find them, it has to be able to use them. So the thing is, we don't have to feed it the rules, right? Remember the example I gave of the rule-based systems. We don't give it the rules, and we don't give it like, this is a list of argumentation pro and this is a list of negative. We just give it texts that it needs, yes. And sometimes we use a crowdsourcing to do that. So there is an example of crowdsourcing argumentation. But once it has that, it can auto-detect itself, and how to use those points in a debate. So that's what we can do today. And I think there are like 100 topics already in there, and new topics can be added. I think it's interesting, again, to have a broader point of view on certain things. It's fascinating.
But you basically have to train it on the topic, no? I mean, should be
You
clear,
have to
no?
give it information about a topic. And then it trains itself. I think that is the distinction I would like to make. It does not go out in the world and I mean, we're not there. It's not like the all-knowing thing. We have to be realistic. So that's a good question in the end. So let's face that, but we have to give it texts in which it can discover arguments. I think that the achievement here is that it can discover those arguments in the text and know that it's positive or negative arguments. It can cluster them and then it can use them. That is basically, I would say, the core. That is an achievement by itself. But don't imagine a smart system that just knows all these things, right?
Can I just give an example? Because the dream was, when I studied, was to make a legal expert system. And of course, one can now use this debate machine for doing legal debates. I mean, you can train yourself as check if your legal arguments are good or not. Could be a self-training before you go in court or whatever. No? Because it was always a dream. There was an old time in the 80s was like, okay, we're going to just feed it all the rules and then it knows everything, and we're going to have the expert system, and it's going to be, it will finally bring all this jungle of different laws and regulations around the world. Finally, we'll solve it. Still a dream.
Yeah, I think legal texts and precedents are a good example of data that is self-contradicting sometimes, and that is not complete, and that is not always clear, right? I mean, that's just how it is. And we are already doing a lot of work in trying to automatically structure and make searchable legal texts. So I think this would be an excellent domain, yes.
Yeah. So here comes Yin Chen. Hi, Yin. Very interesting talk. Question about machine learning. It's a black box. We don't know what the machine learned. How can we trust the results from the learning? So it's basically, again, can we trust?
It's a big problem. And the trust element is one of the biggest we need to solve. And indeed, the black box problem, as we know it, is a hard one. We are doing a lot of work on explainability. How can you explain such a network? One of the, I talked about that a little bit in combining symbols and neural networks. We can look at the symbols and understand them, so we can use that. Other techniques are where we try to create a simplified model. So you have a neural network, but from that you deduct a rule-based model that you then can understand. So that helps. Although you have to say immediately that since it's a simplified model, it may not capture all the nuance and subtleties of the neural network model. Because if we could solve the problem with rules, we would do it. So we use a neural network, but then we try to, from the neural network, again, create rules, because rules are the only thing we can really understand. And we can create a decision tree, and then we can follow the tree, and we can see that this works. And this is fine with small problems, but if you have a huge decision tree, even then you can no longer understand. So it's a hard one, right? What we say is that there are a number of things you can do. You can detect bias, for example, in your models and in your data. You can get confidence scores on that. And what we say is you need to put that in your pipeline. So if I'm in a company and I create AI that I want to put in production, and my clients will use that, or I will use it for my own decision making, then I need to include steps to try to understand and follow and monitor the accuracy of my network. And so if I don't put that in a automated pipeline, it will never work, because you will not be able to do that every time. It's too labor intensive. Because as we know, you need to close the loop. So a neural network is trained, a model is in production, and I have to retrain it because the data changes, right? So I have to do this, I don't know, every month or depending on your problem. So you need to automate what you're doing. And in that include checks against bias, for example, and checks for explainability into the process. It cannot be an afterthought, right? It has to be part of your process of it has to be part of the way you work.
Yeah, conceptualizing. Yes, and now I have a question myself. Before that similar question comes from Emma again. I mean, you mentioned these analog chips, and you say you're using this hardware because you're saving energy. But aren't you having gigantic? Don't you need a gigantic space for this? If you need, no?
These chips are very small, eh? So they are not larger than a normal computer chip. So it's the same. It's the same thing. So it's also miniaturized. It's also so that is not a challenge basically.
Yeah.
One of the challenges that are real with analog chips is accuracy. Of course, an analog. I mean, we love digital because it is precise, right? I mean, something is a 0 or a 1, and there is no discussion. In analog, you have a signal, right? And so it is harder to get accurate results. And so there is a lot of work now being done on how can you make the noise that is in an analog signal, how can you control that, and how can you get accurate results from basically what is an analog, therefore not so accurate calculation. So that is one of the challenges that we're trying to fix now.
Yes, and I mean, I just Emre asked similar. Emre, the analog AI chips you mentioned, is there a roadmap timeline on their commercial availability? What about the software stack and compatibility? Do you think there'll be an open software ecosystem around those chips?
To be honest, I don't know. This is really this is research, and with research we don't know. This is not. I don't know about commercialization and how this will work. I don't know if that's something that IBM will do, if it's something we will do with partners. You know, many things are possible. So I don't know about the timeline. I think we are still very much in the core research phase here, in which you are trying to solve some fundamental problems before you can think about commercialization. So we are not there yet. So what I talk about here, and I mean, it's fantastic to try to look a bit into the future, but it's sometimes harder to predict when something will come into reality, because it's a research track. That's why I mentioned quantum computing and the roadmap that we now created, which is new. Up to now, we didn't give kind of a roadmap on quantum. We said, you know, we released a new machine and a new machine, and then it came when it came. And now we changed our approach, and now we are telling the market, you know, by 2023 we'll have 1,000 qubits. So now we have a roadmap, right? I mean, this is different. So this seems to have been, this is moved from pure research into something that's coming closer, but there's all kinds of gradations, and I don't think analog computing is still, I think it's still very much in the core research part.
Yeah, so I'm sorry, time is flying away as always. So it's a super interesting cafe. I have about 20 questions more. So, but as we always try to make it 1 hour, I thank you again, Wouter. Thank you very much. And if there's more questions, I will forward them to you. And if you feel like you can answer them per email.
All right.
And
it was a pleasure, Carmen. Also in the preparation, I must say, you were an excellent host, and it was a pleasure to talk to your team, to your cafe, to your audience today. So I'm looking forward to maybe more questions. Don't hesitate to contact me or follow me on Twitter or something, where I broadcast all these crazy things.
Yes, and then just in 1 minute, I just announced for anybody who feels like coming back to the cafe on October 7th, we have the next live speaker. It's always before the universities don't start, it's a slow beginning of the cafe. Then in November, we're gonna have more than every week. So it's always like a slope. But the next one is on October 7th, and the live speaker will be Sheila Belaniyat, and she's the global head of partnerships for women in AI, with her talk on accelerating AI for women. So you will, of course, all get an invitation automatically, and you can even forward it to other AI enthusiasts, because cafe is open and free. And so thank you for being here, and have a nice afternoon, and see you soon again. Thank you. Bye-bye, Wouter. This was a pleasure.
All right. Bye-bye.
Bye-bye. Bye-bye.